Hello everyone, I'm Christian Duran. I am going to introduce the work named Routing-Aware Standard Cell Placement Algorithm Applying Boolean Satisfiability. I'm part of the Universidad Industrial de Santander WIS in the Integrated System Research Group on CHIP. For the outline of this presentation, first we'll present an introduction about the standard cells and our work. Then we will define the placement formulation of the creation of the standard cells. Optimizations will also be defined next, and then finally we'll present the layout generator with some results. We will now hop to the introduction. To create digital circuits, we execute several processes including synthesis and place and route. In the right is a synthesized net list. We will be placing and routing using several grids pictured in the left. For this reason, we use standard cells. Several cells perform different kinds of functions and logic. The synthesizer previously mapped the RTL circuit to those circuits, offering a netlist whose behavior resembles the intended netlist supplied in hardware description languages. The next step is to perform a placement and routing to implement this circuit in VLSI. The placement of standard cells follows a grid, which is usually defined by the smallest cells possible. Other nets have a horizontal size, which is a multiple of this minimum size. Another grid is defined to perform routing. These routes will integrate the circuit in the intended behavior according to the netlist. Each one of the standard cells contains ports where the routes can connect. These grids are defined by the technology design rules. Now, this is how a standard cell looks like. To create a standard cell, the height and width of the circuit are multiple of the previously defined grid. We call this grid the horizontal and vertical pitch. Although the grid is established, the internal routing of the standard cell does not usually follow this rule, with the intention of being as compact as possible. Instead, the ports are the only ones that strictly necessary to match this grid. This is due to the place and route algorithms which follow the grid and only connects ports between standard cells. Falling back to the standard cells, these circuits are contained within a library. These cells contain different functions such as gateway logic, compressed logic, multiplexers, latches, different kinds of flip-flops, and balancing and echo cells. To create this standard cell library, we implemented a procedure where automatically extracts design rules, designs topologies, generates and characterizes the circuits. The process to create this standard cell library we follow is as such. First, an initial configuration is performed, which contains the number of tracks, defining the standard cell height. Along with this step, an extraction is performed to list and save relevant design rules for the standard cell layout generation. Next, we generate the netlist of the standard cells. In this step, the scripts perform several simulation cases to define the sizes of different transistors according to the topology. This will constrain the topology for place and route purposes. When we have the standard cell library, we characterize it and verify it, and ready to be used in an EDA tool for placement and routing of VLSI circuits. The main problem with these standards that we want to focus and we want to solve is the standard cell layout generation. Having the schematic in netlist form from the previous step, we perform placement and routing of the designs. The main focus of the solution is a position algorithm in double row for standard cells. For this algorithm, we define a series of rules and constraints for finding the minimum width position of all transistors inside the cell. Also, with the purpose of outputting a layout, this solution needs to optimize for net congestion for routing purposes. With this problem established, we are going to go now to present the placement and routing for standard cell layout generation. First, I will introduce Boolean satisfiability. Given a Boolean expression in conjunctive normal form, a Boolean satisfiability algorithm will look into a combination of inputs such as the output is true. This is considered as a satisfiable solution. Because the Boolean expression is in conjunctive form, each of the multiples is considered clauses. These clauses can constrain the variables to avoid certain bit of combinations. In this example, if you put the clauses in red, you are avoiding that the value of a, b, c is specifically 0, 1, 0. In Boolean satisfiability, all the constraints must be true to have a solution. Now, I will introduce you to the algorithm through an example. This is a typical schematic for the latch, which consists of the enable splitters, the latch, and the output logic. In this design, the number of P and N transistors is the same. We extract the numbers of transistors and the number of nets in the circuit. For this algorithm, we are going to position all the transistors in a double row architecture. The minimum number of columns for the positions is constrained by the maximum transistor in P and N rows. For this example, we have 9 initial columns. From here, we start to define our positioning variables. For each of the transistors, we have a flip state, for example. If the value is 0, that means that in the order of the connection is drain gate source. If it's 1, it's the opposite. Next is the position of the transistor. We have here 9 columns, so for each transistor we define 9 variables for positioning. A value of 1 indicates an instantiation of the transistor in such a column. From here, we have the positioning defined. So we now need to constrain double instantiation of the transistors by not letting 2 position variables to be in one at the same time. For every transistor and any pair of positionings K and L, we close them to avoid to both being active. Now, we avoid 2 instantiation of 2 different transistors in the same position. For any pair of different transistors I and J, and any position K, we constrain that both are active. We assume that positioning the transistor next to each other means that they are avoidable. This means that the net in the middle of 2 transistors needs to be the same. In this case, we iterate any kind of transistor I and J with any position K. We also iterate both flip states, and if the extracted net is different in the middle, we constrain this combination with the position of the both transistor and the flip states. When we define the previous positioning clauses, we evaluated satisfiability. If the current clauses are not satisfiable, we increase the number of columns until it's satisfactory. With this procedure, we guarantee the minimum number of columns necessary to realize the circuit. Until now, we have the positioning of transistors. Now we are going to talk about the optimization for routing awareness. Vertically, we wish for common gate signals. If so, the routing for many nets can be done using polysilicon. We define optimization variables for each column, which determines whenever the gate is different. We iterate a pair of PN transistors I and J. Then for any position K, if the gates are different, that means that the optimization variable cannot be 0. We perform a similar thing using different diffusions. With this, we intend to reduce the net congestion. We iterate a pair of PN transistors I and J, and with a position K and a side S, whenever the flip state makes the certain sides nets different, the corresponding variable cannot be 0. Having a specific positioning for the transistors, we can extract the location of pins as variables. For each net, we create a set of variables that locates the pin position according to the transistor instantiation. To determine the position of the pins, we iterate all the transistors in I, and for any position K and psi S, whenever the flip state makes the net appear, the variable is constrained to not be 0. With the previous pin variables, we now can determine the horizontal span of a net in terms of Boolean variables. This will add route awareness to the current formulation. We make use of 2 additional sets of digital variables for this purpose. One of them will detect the leftmost connection and the other one will detect the rightmost connection according to the pin variable's positioning. This is the complete formulation for the positioning of the nets in this work. For the leftmost detection, we iterate any net j with any position ks. Then, any iterated position k prime s prime that is greater or equal to ks will be constrained to not be equal to 0. This will make all the variables to forcibly to be in 1 whenever the leftmost position is detected. We perform the opposite for the rightmost detection. So, for any position k prime s prime that is less or equal to the current position ks, will be constrained to not be 0 if the pin is active. Finally, for the horizontal span, we perform AND clauses between the previous side detections. For any position k and psi s, if both leftmost and rightmost are active, we constrain the horizontal span to not be 0. From here, we use pseudo-Boolean satisfiability to progressively find the optimization. Pseudo-Boolean satisfiability allows us to introduce an expression as the minimizer, which constantly is finding the lowest value according to the solver variables. With all previous net clauses, we minimize 3 kinds of expressions. First, we wish that there are few different gates as possible. We input the sum of different gates variables as an optimizable expression. Then, we also optimize the different functions. The sum of different function variables is introduced also in the optimizer. Finally, to reduce the horizontal routability, the horizontal span of all nets j are summed all together and introduced in the final optimizer. When an optimum is found, the transistors are arranged in 2 rows. Each transistor that is next to another presents an abutment. This is the final result of the placement algorithm. With the placement solved, we move to the layout generation and show some results. To evaluate the quality of placement, we performed a benchmark for evaluation of the road congestion. The vertical placement for transistor is accommodated in the innermost possible position. From here, we create a grid using the gates and the diffusions. Each pin of this grid is assigned with a number of each net. The positions of the pins are marked in 1, as the road is always going to pass through the pin locations. So other positions within the pins are marked with, we assign it using an additive multiplicative expression, reflecting the probability of the net passing through that bin. Next, we perform a sum across all the columns for all the nets. And the final congestion is a weighted sum of the average congestion and the maximum congestion of all columns. We executed this algorithm in several cells with the original positioning algorithm and the optimized one. For simple cells like OR and AND, the results are very similar. More complex designs tend to have progressively better congestion. The routability of the cells increases in 30% of the cases, reaching 100% of the routing in some cases. And now, using maze algorithms, we routed the designs and gave a layout for all cells. Here are some examples that include a 3-state buffer and latch that we saw previously. So, as concluded remarks, we provided a standard cell generator with the linkage of several procedures. These ones include the netlist generation and the DRC extraction. We link the placement and routing by optimizing the net horizontal span using satisfiability optimizations. Finally, we were capable of offering more routing in 30% of the cases where the algorithm was tested with better congestion metrics. Here are the references for this presentation and for the paper as well. Thank you very much.